Alright, chemistry. We had a minor delay. However, we are back to a schedule. So, finishing C Day, talking about, we're on C Day, right? But we're talking about atomic structure, atomic concepts. We finished talking about this last, whenever your B Day was, right? Uh, Talked about this, took a quiz on B Day, so I guess actually we talked about this on A Day. But took a quiz on B Day, and then we went right to this. Protons, neutrons, electrons, what's in the nucleus, what's on the outside, how is everything charged, right? Nothing crazy, nothing new. I know that the next page, which was page 13, has a couple of practice, has this nice little chart. The chart's in color on the PDF. It's black and white, obviously, with the copies. Um, I don't know how much more useful the color version is. We have this diagram, which we will talk more about. It's a little out of date, but that's not a big deal. It's a good enough approximation for right now. Now I am going to actually skip all the way to page 14. I'm going to start here talking about some atomic models, some atomic theory, from experiments that were done. Going backwards a little bit before we go forwards, just to give you a little timeline of stuff that happens. All right, the first blank here is for a name. And the name is Dalton, right? John Dalton. He came up with, we attribute him with one of our first atomic theories of matter. And it said a few things. A lot of what he said was right. He got a couple of things wrong, but win some, lose some. Right, he believed that every element was composed of small particles called atoms, so that was fine. And he believed that all atoms of a given element were identical, but they're different from other atoms of other elements. So far, actually, we're doing pretty good. He's kind of 2 for 2 here. He bought into conservation of matter, so atoms are neither created nor destroyed in any chemical reactions. We're not making stuff, we're not getting rid of the stuff entirely, it's just shifting. Right? And a given compound always contains the same type and number of atoms. So something like water is exactly H2O. It's 2 H's, 1 oxygen every time. No questions. Again, he's doing real well. This last part is where he kind of goofed. He said that at the time, right, there were about 100 elements that they knew about, so there must be about 100 different kinds of atoms. He believed that they fundamentally differed from each other. So a carbon atom was different from an iron atom, was different from hydrogen. Nowadays we know they all more or less look the same. They differ in size, they differ in makeup a little bit, but they're not literally different things. Right. This next bit looks like it's breaking up the page, but it's here for the title of an experiment. Right. It's the Rutherford gold foil experiment. There's a person named Rutherford, first name Ernest. He did an experiment using gold foil. He didn't do it because gold was shiny and he wanted to impress everybody. It was helpful to do it shiny, but mostly because gold is a very soft metal. When you want to make something out of gold, you actually typically combine it with something else. But gold on its own is very soft. It's easy to turn into a foil. So what he did was he took gold, he hammered it into a sheet. He'd wanted to get it so thin that it would theoretically only be 1 atom thick. That way he could kind of determine some stuff about the atom. Now, did he actually get it 1 atom thick? I have no idea. I wasn't there when he did it. But he got it thin enough and close enough and came up with some pretty interesting conclusions. So, our boy Rutherford, Ernie, Rutherford, he bombarded a piece of gold foil with what are known as alpha particles. Alpha, like the first part of the word alphabet. So he sets up his gold foil. He's got a particle gun. He fires the particles at the gold foil, He's got sensors all around this room, all around this chamber. Really, it's not quite a room. And he just wants to know where they go, right? Do they hit it and bounce off? Do they kind of pass straight through? What happens to these alpha particles? And what he found was that actually a lot of them do go straight through the foil, which is important for the next bit. The other thing that he found was that a few of them actually got deflected. A few of them did not stay in that same straight line path. Came up with two things from this. There must be something inside the atom that is small, densely packed, and positively charged, which we now know to be the nucleus. It had to be small and densely packed because that's the only way that these particles would bounce off or deflect. It had to be positive because if they were negative, the particles would get stuck and they would stop. There would be no detection over here, or over here, or over here, wherever they ended up being deflected to. Secondly, because most of the particles went straight through the foil, a heck of a lot of the atom must simply be empty space. This is a big deal because before, Dalton, there were a couple of guys in between Dalton and Rutherford. We don't give them a lot of time here, but there were a few people in between. They thought that the atom was just this thing, right? And then it was next to another thing, and it was next to another thing. Now, Rutherford figured out it's a thing, yeah, but then there's a bunch of empty space, and then there's another thing. It was these nuclei. Now, in between these two fellas, there's another guy named Thomson. Occasionally, his name comes up. He came up with the concept of electrons. You really kind of only need to put these guys in a timeline. Occasionally you'll need to associate Rutherford with his experiment. But, just in case, I'm mentioning Thomson. He talked about electrons. Our next gentleman is Niels Bohr. He comes up with a model of the atom. And it's focusing on electrons. Again, that guy Thomson mentioned electrons. Rutherford figured out there were protons. He didn't, I don't know if they called them protons yet, but figured out there was a nucleus. There's something positive in there. That was the proton. So Bohr wants to focus on, well, what's on the outside? What's out there? So he made a model that focused on where electrons were. Excuse me. And where they were, he believed, was following circular pathways at fixed distances from the nucleus, which is basically they orbit the nucleus, which is why sometimes you might see this called the Planetary Model. That's not how you spell planetary. I'm so sorry. That's much better. Well, it's better. But much like planets orbit the sun, Bohr believed that electrons orbit the nucleus. Now this is where our reference table comes into play. We talked before about the atomic about the atomic number, and I mentioned the atomic mass before up here. But now I want to focus down here on the electron configuration and what it tells us. It tells us a handful of things. One, it's another way to remind us of how many electrons there are. Take the numbers in the electron configuration and add them together. You'll always get the same number as the atomic number. It's because the number of electrons in an atom is the same as the number of protons. This is not a minus sign in between them, it's simply a dash. It's separating the two numbers into levels. So here for carbon, I have 2-4. That is representative of an energy level with 2 electrons and another energy level with 4 electrons. If I were to look at aluminum, I would see 2-8-3, which would be to say 2 electrons in the first level, 8 in the second, 3 in the third. Each level progressively gets further away from the nucleus. So the first level, if this represents the nucleus, first level might be here, orbiting like such. Second level might be here, orbiting like such. Third level might be here, orbiting like such. Alright, so it's getting progressively further and further away. Each element has an electron configuration. You'll notice that there are slightly different amounts of electrons in each. One thing to take note of, right here at number 72, there is an asterisk, and it looks like there are only 4 numbers. However, this asterisk is very important. It leads us to a small note. Oop, runner. Oh goodness. Please. There we go. That asterisk says the presence of 2-8 for all elements number 72 and above. And what that means is really all that happens, they ran out of room at the bottom of the box here. But this is 2, 8, 18, 18, 9, 2. This is not simply 18, 32, 10, 2. It's 2, and then 8, and then this. Which is why you'll notice everything after that starts, I put that in quotation marks, starts with a dash. Because before it, there's a 2 and an 8. Right, so the first level for this element has 2, second level has 8, then the third level has 18, fourth has 32, fifth has 11, sixth has 2. Right, and you'll see that that happens in all of these ones down here. That's why that dash is there. All right. So just something to be a little cautious of, something to be a little wary of. There we go. But that's the electron configuration. So we've covered all the numbers on the left. We'll cover the numbers on the right on D-Day. Now, back to our notes. The reason I bring this up is because with Bohr, we have what we call Bohr diagrams. Now, the Bohr diagram represents a visual of the electron configuration. The circle here represents an energy level. Here there are 2 circles, 2 energy levels. Here there are 3 circles, 3 energy levels. The energy levels are populated with electrons, which we represent with dots. Helium has 2 dots because, if I look, helium, right here, has an electron configuration of 2, which says there's only 1 energy level, and on it there are 2 electrons. Carbon is our next one, has 2 dots and 4 dots for 2 electrons and 4 electrons. So, if I do this, I'm going to have 2 dots on the first, I'm going to have 4 dots on the second. You might notice that I'm spacing out the dots. It's because they're runner. It's because electrons are all negatively charged. So they don't actually want to be near each other. Much like magnets would repel, right? Like sides of a magnet would repel. Same thing happens with charges. Like charges will repel each other. Got my pen back. Finally, phosphorus. If you were to look for it, it'd be number 15. You would see 2 dots. Then you would see 8 dots. And then you would see 5 dots. And that's phosphorus. Right? Now, Bohr diagrams are not superbly difficult. However, the big thing is to make sure that you have the correct number of dots on the correct levels. Right? There's one piece left to this. We've talked about many individuals, however, we now know more or less specific things about the atom. And it's because of all of those individuals. We kind of compiled all of their information and experimented and theorized and weeded out what was right and what was wrong. We developed what we call the modern atomic theory, which was created by many scientists over a long period of time. It states that atoms are composed of protons, neutrons, and electrons, nothing new. We call them subatomic particles. We know that the nucleus contains protons, which have our positive charge, and it contains neutrons, our neutral charge. Protons have charge equal in quantity to the charge of an electron, but the sign is opposite. The protons are positive, electrons are negative. Electrons have little mass, functionally zero. Neutral atoms, number of protons is equal to number of electrons, and the masses of all those subatomic particles is expressed in what we call atomic mass units, or AMU. The modern atomic theory, which is one name, or the wave mechanical model, states that the most probable location, the most likely location of an electron is actually called an orbital. Right? It's not an exact orbit, it's not an exact circle around the nucleus. It's kind of this area. If this represented the nucleus, then the first energy level, the first place you would find electrons, is not exactly this circle. It might be just kind of this general area, right, where my hand is kind of just going around. Second energy level will be further away, it'd be kind of out here somewhere. This is where we would find the next set of electrons. Being familiar with this is really just an extension of this information. All right. Now, for D-Day, whenever your D-Day happens to be, I would like you to answer some questions from the Orange Review book. Now, I am working off of a slightly outdated version of the review book, so what I'm going to do is I'm going to put down page numbers and question numbers. However, please use the pictures attached to the assignment. You will see them very clearly. I will attach the pictures, and in the description, you will see which questions to do. Alright, it's practice multiple choice questions on this stuff that we just did, and a little bit of the stuff from page 11. Alright, or actually page 12. Alright, we'll keep going. We'll talk about ions and isotopes on D-Day, which is going to help us, which is really going to let us finish talking about all the numbers on the periodic table. So you will have at least a cursory understanding of like when to use any of these numbers. All right. Until D-Day, I'll see you around. Take care, chemistry.